Hello, hello. Last time we were talking about the evidence for the Big Bang Theory, meaning that we were talking about evidence that the universe had a beginning, that the universe has not always existed, but it actually began to exist sometime about 14.8 billion years ago. Now we're going to talk about the things that we find in the universe, more specifically stars. How do they form? What are their life cycles like? How do we classify them? That's what I'm going to be talking about here. So first to begin, what are the different parts of a star? Well, a star has a quote-unquote atmosphere, and there's different layers to those atmospheres. So at the very center, we have the core of the star. The next layer kind of out is the photosphere. Now the photosphere is notable because it is the part of the star or the sun that you can see. That word photo is a word meaning light or visible. So that's the part that you can see. It's about 400 kilometers thick. Next, on the outside is the chromosphere. You can't see this with the naked eye. Don't try to look at it either. That'll burn your retinas or something. But this is only visible during a solar eclipse. We have to block out the rest of the sun in order to see the chromosphere. And then finally, on the farthest outside, we have the corona. This is also only visible during a solar eclipse. We can kind of think of the corona as the rays of the sun coming outwards. So here is kind of a take on the layers of the sun. You have the core in the middle. You have the photosphere here on the outside, the chromosphere a little bit outside of that, and then you have the corona out and around that. Here's a picture of a solar eclipse, and here you can see the corona. It's pretty obvious here. It kind of looks like a lion's mane, and you could only see the corona during a solar eclipse. We want to ask the question, why are some stars bright and hot, and why are other stars cool and dim? So there's lots of different stars out there. What are the differences between them, and how do we know those differences? So there is a deep connection here between the temperature of a star, its energy output, and the diameter. And the relationship between those three things are its mass. So the higher mass a star is, the bigger it is, the higher temperature and energy output it has. The diameter, so how big the star is, this also depends on the stage of life the star is in. Now, just a disclaimer here. When I say the bigger a star is, the higher temperature it is, I don't mean that as an absolute statement. So there are exceptions to this rule, and we're going to talk about some of those exceptions. But generally speaking, the bigger a star is, the hotter it's going to be and more energy output it's going to have. Now, where do stars get all of this energy to be bright and to be hot? Well, they undergo a chemical process called nuclear fission. And what happens during nuclear fission is that the nucleus of atoms are fused together. They are squeezed and squeezed and squeezed and squeezed so much until they are actually put together into the same nucleus. What it does in the case of our sun and other stars is it takes very small hydrogen atoms and squeezes them together into larger atoms such as helium. Here's a depiction of a fusion process. Here we have two hydrogen atoms combining into a larger helium atom and energy being released as a result. Now, as we're going to talk about, what stage of life a star is in is dependent upon how much of its hydrogen it's used up. So here, if a star has used up a lot of its hydrogen, right, it's taken its hydrogen and converted it to helium. It squeezed the hydrogen together, made it into helium. Well, what happens when it runs low on hydrogen? Well, the star can still operate. It can take the helium and squeeze it together into carbon and oxygen. Well, what happens when it runs low on helium? It can take the carbon and oxygen and squeeze it into oxygen, sodium, and magnesium and neon and other things like that. So what you see here is that as the sun or the star runs out of fuel, it starts making heavier and heavier elements. As we get down here, the longer a star's been alive, the more fuel it's used up, the heavier atoms it's creating. And so here in the middle, we have iron and nickel, and then on the outside, we have things like hydrogen and helium. There's different ways that we can measure a star, just like how we would want to measure a person. So a person can be measured with their height or their weight or their IQ or something like that. We want to measure certain things about stars. So one thing that we can measure about stars is the magnitude. And magnitude is, generally speaking, how bright a star is. There's different types of magnitude. So if you're talking about the absolute magnitude of a star, this is the brightness a star would have if it were placed at a distance of 10 parsecs. Just so you know, a parsec is 19 trillion miles. Now, we can also measure a star's luminosity. And what we mean here by luminosity is the energy output of the star. How much energy is released per second from a star? This is measured in watts. Now, we want to know something. Is a star bright because it's really powerful, because it's really hot, or is a star bright because it's close? And that's why we have absolute magnitude. Now, if we take these things together, magnitude and luminosity, they help us to determine if a star is bright because it's close or because it's really powerful. One of the ways we can categorize different stars is by using a Hertzsprung-Russell diagram. You might hear me call it an HR diagram. These are used to depict what stage of life a star is in. Now, the way we do this is we can compare absolute magnitude, so brightness, or luminosity, so we can compare brightness or energy output to temperature. And you'll see what I mean here in a second. Now, what you're going to see here is that most stars are main sequence stars. What it means for a star to be main sequence is that it has not run out of hydrogen yet. Now, once it runs out of hydrogen, the star is officially in old age, but until then, it is not. So this is an HR diagram. Notice a couple of things. We've got temperature in degrees Kelvin on the bottom, and notice that as we move to the left here, we get a hotter temperature. As we move to the right, we get a cooler one. And over here, we have brightness. And so as we move higher, we get brighter. As we move lower, we get dimmer. And so you can notice kind of 4 distinct groups here. First, we'll talk about this band that goes across the middle. These guys are what are called main sequence stars. So, like, let's say we have a sun, like our sun in our solar system. It has a temperature of about 7,000 Kelvin. Its brightness is kind of in the middle. So, if we line it up here on the HR diagram, it lines up in this band, which means it is a main sequence star and it has not run out of hydrogen yet. So all of these guys can be thought of as middle-aged stars. Now, the next group are supergiants. So why are these supergiants? Let's talk about that for a second. Well, let's look here. We can see that these stars over here are very cool. They're not very hot, but at the same time, they're very bright. So how can we explain the brightness of a star even though it's cool? Well, it must be very big, right? So these are supergiants. These are huge stars that are not very hot, but because they're so big, they're still pretty bright. Okay. We also have giants. So these are very related categories, red giants here. Red giants are about as cool as supergiants, but they are not as bright. Now, down here, we also have an opposite question, right? An opposite question from up here. And that question is, we have these stars that are pretty hot, right? I mean, they're not all the way over here, but they're pretty hot, but they're very dim. So how could that be? And an explanation for this is that these stars are very hot, but they're not very big. and that's what makes them bright. And so those are what are called white dwarfs. So I would look out for test questions and quiz questions where I give you the coordinates of a star, and you have to tell me what type it is. So for example, if I tell you I have a star that is 10,000 degrees Kelvin and has a brightness of 0. So what you would have to do is you would have to go to brightness 0, scroll over to 10,000 over here, and you would see that the star falls in the main sequence, and you would answer that it's a main sequence star. Now, there's some trends that we can actually get from this. Now, what I like about this HR diagram is that it's an HR diagram, but it also gives you the color of the stars, right? Stars burn at different colors depending upon where they are in their fuel burning process. And so let's see if we can kind of get some trends here. What is the relationship between star temperature / color and brightness? Well, we see here that for the most part, as we get hotter and hotter and hotter, the stars get brighter and brighter and brighter. Not only that, as the stars get hotter, they get more blue. So generally speaking, high temperature stars, hot stars are blue and bright, for the most part, except for white dwarfs. Okay. Now, low temperature stars, cool stars, tend to be red and dim, not very bright. The exception are with giants, but that's just because they're really big. What is the relationship between temperature, color, and how long a star lives? Well, let's just think about this for a second. Let's say I have a candle, okay? The hotter that candle burns, the quicker the candle melts. Does that make sense? So that means that the hotter that the candle burns, the shorter its lifespan as a candle. This is pretty easy to understand, I think, especially when we think about candles. So with that in mind, the same relationship applies to hot stars and cold stars. So stars that are hot have a short lifespan because they burn through their fuel very quickly. Stars that are colder have a long lifespan because they do not burn through their fuel as quickly. They're more of a slow burning fuel. Now, the stages of life that a star can go through depend on how big the star is. So we're going to see in just a second, you're going to see the lifestyle of the star, and you're going to see a couple of forks in the road. And we're going to talk about those forks in the road, about what path a star will go down depending upon its size. So all stars, no matter what their size, start off as nebulas. And what nebulas are is they are these big clouds of gas and dust in space, and these are known as the birthplaces of stars. Now, sometimes what will happen is that this dust will start clumping together, and you'll kind of get a gravitational pull, and it'll form something called a protostar. So it'll be kind of a cloud, a nebula, with a dense sort of clump of gas and dust in the middle. This is what's called a protostar. So here we go from a nebula to a protostar with things kind of gathering up in the middle here. Now, when the protostar gets big enough, it'll begin the process of nuclear fusion. And remember, that's the process of taking two hydrogens, putting them together to make one helium atom. Now, at this point, we have a fork in the road. If the protostar forms a small star, then that small star will burn through its fuel, and it will eventually become a red giant. So this path right here is actually the path that our sun is on. So our sun will go through this path. The red giant, as the star runs out of hydrogen, it gets bigger and colder. Well, yeah, so as it starts burning things other than hydrogen, the sun is going to expand, and it's going to get bigger, and it's going to get colder. Therefore, it will be a red giant. Now, eventually, that expansion will go so far that it'll return to kind of a cloud-like shape, and this is called a planetary nebula. Now, at the center of that planetary nebula will be kind of the core of the sun, or a small, dense star that'll remain in the middle, and this is called a white dwarf. But what if the star is large, right? If a star is large, then instead of becoming a red giant after it runs out of fuel, it'll become a red supergiant. And what this means is that the helium that's produced is going to keep being combined into heavier and heavier elements. Now, that is until the star goes supernova. Now, during a supernova, the star collapses in on itself and forms a neutron star. That's one thing that can happen, right? And during this supernova, what happens is that the gases and particles and everything kind of collapse towards the center and then bounce out and explode outwards, right? So that supernovas are kind of big explosions. Now, the result of a supernova can either be a neutron star or it can be a black hole. Now, a black hole is a star that is so dense and so big and has such strong gravity that not even light can escape from its gravitational pull. So here's our path, right? We start with a nebula, and then we have a fork in the road that is based upon the size of the star. If the star is small, it'll become an average star, a red giant, a planetary nebula, then a white dwarf. If the star is bigger, it'll become a massive star, a red supergiant. It'll go supernova, and the result of that supernova will either be a neutron star or a black hole. Thanks for watching, and I hope that was helpful.